Welcome to 8-6, square roots and cube roots. You may know all this. You might be very comfortable with this material, in which case I would suggest you come to me for a quick assessment of your knowledge of it so you can move on to the next lesson. This is rather long, that's why I'm suggesting that. If you're not real comfortable with this, I would do a quick scan of the material. Go through the lesson, because there are some very important concepts here that you're going to need as we move into the next chapter. So this is not something to just skip because you want to skip it. Make sure you know it. Know the vocabulary. It's right up there. You got to know the difference between squaring something and taking the square root, cubing something and taking the cube root. We've got our big idea and our definitions for square root and cube root. And we also have the square of a square root property. One of the things to be clear about when we're talking about square roots is if I ask for the square root of 25, I'm asking for the positive square root of 25. That will equal 5. If I would like to, the negative, I would write the negative root 25 equals a negative 5. And in this way I differentiate when using a radical. There are, for something like 25, there are two roots, 5 and negative 5. There are two square roots for it. So when we talk about the roots or the principal square root of something, we're talking about the positive value. I would differentiate this from the problem where I have the problem that says x squared equals 25. While I'm going to take the square root of both sides of this equation, I need both the positive and negative root in this case because I'm coming at it from x is squared. If x is squared and equals 25, it could be either 5 or negative 5. Different approach to the problem. This is our starting point where we need to consider both roots. When we're using just the radical, we're looking for the positive root of the value, of the number. With cubes, we don't have that problem. But what we get here is that if I have the cube root of x times the cube root of x times the cube root of x, this is equal to the cube root of x cubed, which is equal to x. You might ask why we don't have the 2 with the radical for the square root. The reason for that is this is just so commonly used that people look at it and take it to be square root. So we don't need it. It's an unnecessary notation, where if we're going to take any other root, 3, 4, 5, 10th root, whatever it might be, we need to indicate that on our radical symbol. One of the things that's interesting, if you remember our properties previously, that if I take the square root of something, and then it's equal to the square root of x squared equals to x, well that's x to the first power. And if that's x to the first power, then that must be saying something about what power is being indicated in the previous problem. So if that's x to the first power, let me get rid of the this 2. Okay, that's x to the first power. So x to the first, and that equals x squared raised to, well, what 2 times what's going to give me 1? 2 times its reciprocal, right? 2 times a half, and that equals x to the 2 over 2, which is x to the first, which equals x. So the symbol we're going to use for a power is, for the square root, is 1/2. Well, what do you think it's going to be for the cube root? We have the same result, that x to the first power is equal to x cubed raised to some power, and 3 times that has got to equal 1. Again, it's the reciprocal of 3, which is 1 over 3. This equals x to the 3 over 3, which is x to the first, which equals x. Okay, on to the next part. Got a quick activity. Follow these steps to determine the area of the square EFGH at the right. I want to know the area of this square EFGH. So I know perhaps something. Step 1 tells us that the square ABCD is 3 units on a side. What is its area? So ABCD, it's a square, 3 units. So the area of a square, area is length times width. Length times width. It's a square, so all sides are the same. So area equals 3 times 3, which is 3 squared. So the area of the ABCD equals 9. Step 2. Triangle AEH is a right triangle with legs of length 1 unit and 2 units. What is the area of AEH? Well, the area of a triangle is equal to 1/2 the base times height. We know the length of base and we know the length of 2 of the legs, so 1 is the base, 1 is the height, so the area of the triangle is equal to 1/2 times 1 times 2, which is equal to 1. Subtract the area of the 4 triangles from the area of ABCD to get the area of EFGH. So what we're doing is, if we're subtracting out these 4 triangles, those are areas of the rectangle that we are, of the larger square that we're removing. The area that's left is this internal triangle whose area we'd like to determine. By doing that, we'll subtract this. So this is 4 times 1 is our area of the triangles, all 4. So I have 9 minus 4 times 1, which is 4, which gives us that the area is 5 units squared. So we've taken this concept of areas and used it to determine this internal area of EFGH. What's the length of a side of this internal square? So what does EH equal? Well, EH equals, if this is 5 units squared, then EH is equal to the square root of 5. Because to get the area, it would be EH times HG, whatever. So square root of 5 times the square root of 5 equals 5. We know that from the properties we had before. So this is our exact answer. EH equals 5. Well, what is the square root of 5? Do you have that value available? Now what you're going to find is that you don't get an exact answer for the square root of 5. If you plug that into your calculator, you're getting a long, non-repeating, apparently non-terminating decimal. And so if you were to write it in decimal form, you would write it as an approximation, because the exact form is root 5. That's the exact length of EH. The approximation of that length would be, you could say about 2.24. Depends on how many decimal places you want to go to. That would be an approximation. We distinguish between exact answers and approximations. If you're asked what something equals, that's an exact answer. You need to carry the square root through it. You cannot use an approximation. Onward. Okay. What are the square roots of each number? You'll notice it says roots, plural. We've just talked about this. So what's the square root of 121? So the square root of 121 is, well, that means what squared is 121 is equal to 11. Well, that's one root. What's the negative square root of 121? And that equals to a negative 11. So our answer is 11 and negative 11, because a negative times a negative is a positive, is 121. What is it for 13.5? 13.5 is equal to, and can we write this as an equals? If you put this into your calculator and you get it, or do you get something that you could write an exact answer for? And I think if we 13.5 square root 13.5, it doesn't look like we're going to get exact answer here. So our exact answer is plus or minus the square root of 13.5. Our approximations are going to be plus or minus about 3.67. Yeah. And that's our approximation for the square roots. And we've got two choices there. Again, if you're asked for an exact value, you're stuck with using the root for something like this. If you're asked for approximately or about, then this approximation would work. Okay, wanted to just reiterate that with the statement here. If two numbers have the same absolute value, such as 3 and negative 3, then they have the same square, 9. Although negative 3 cannot be the length of the side of a square, every positive number but 0 has two square roots, one positive and one negative. We denote the square roots of a by the symbol the square root of a, the positive root, and the negative square root of a, the negative root. So the square roots of 9 are the square root of 9 equals 3, and the negative root of 9 equals negative 3. The two square roots of 5 are root 5 and negative root 5. In the figure on the previous page, our GH equaled the square root of 5. It was a positive root because it's the side length. Okay, take a look at activity 2 in your book. This is on page 490. It says use a calculator to verify that x to the 1/2 equals the square root of x. So we enter 16 raised to the 1/2 power. What number results? And what did you get? You should have gotten 4 as a result. You have calculated the square root of what number? You've calculated, based on this, that the square root of 16 equals 4, and you've shown that 16 to the 1/2 power also equals 4. Enter 8, and what number do you get? And again, are you going to get an exact answer? If it's an approximation, we'll do it to 2 decimal places. So root 8, and it's about 2.83, so approximately 2.83. And you have calculated the square root of what number? You've calculated the square root of 8 is approximately 2.83. Next one, enter a negative 4 raised to the 1/2, and what results do you get, and why do you get it? Oh, wait. Go ahead and do it, please. Okay. Now you may have gotten two different results here. If you've got a negative 2 as your result, you did this wrong. You didn't put the parentheses around the negative 4, and what you got was the negative root 4. So this is equal to the negative of the square root of 4. Which is not what you were asked to find out. You were asked to find out the square root of a negative 4. And this should have given you an error message. And the reason for the error message is there is no real number that is a square root of a negative number. We're going to learn in our next algebra course, Algebra 2, about imaginary numbers and how we apply those. For now, this should have been your answer. If you got this first one, remember to be careful about your use of parentheses and how your calculator works with negative symbols. Activity 3 says use the idea of activity 1 to determine the length of the side of the square IJKL shown below, side of the square. Sorry, I cut that off. So if I want to figure these out, I can use the information from this grid to determine the lengths of the triangles. Well, an IJ is the hypotenuse of a triangle. That would be, I'm going to call this letter A. So IAL has an area, so area of IAL is equal to 1/2 the base, which is 2 units, times the height, 1, 2, 3, 4, 5. Well, 2 times 5 is 10, half of 10 is 5, or the 2's cancel, and I get that the area of this is 5. I can take this information to calculate the area of this larger figure, and I need to just simply know what this is 1, 2, 3, 4, 5, 6, 7. So the area of my large square is equal to 7 squared, which is equal to 49. So we'll make that A, B, C, D. So we've created this larger square, and we're using the grid to do our calculations. And so now I've got that this is equal to 49, and I'm back to subtracting this. How many of these triangles with an area of 5 do I have? It's 4. So it's 49 minus 4 times 5, and 4 times 5 is 20. 20 from 49 is 29 units square. So that's our our area for that. So if that's our area and this is a square, then the length of a side, IL, is equal to the square root of 29 is the length of a side. Now I could approximate that, but right now that's all I need to know. It is equal to the square root of 29. Okay, that's activity 3. Let's take a look at our next activity. And here is activity 4. We have 3 squares are drawn on a coordinate grid at the right. Use the idea of activities 1 and 3 to determine the area of square 3 and explain your work. Well, what is the area of square 1 is kind of a first step here. And square 1 is, well, it's 5 by 5, so this is 25 units squared. Square 2 is 6 by 6, so that's going to be 36 units squared. And if that's true, well, let's see, I need to go back and do number 1. I jumped ahead. Use the idea of 1 and 3 to determine. So I need to know what the area of this triangle is so I can subtract it from this larger triangle. And this is going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So that's A, B, C, D. And we've got our larger square, so the area of ABCD is equal to 121. It's 11 squared equals 121. The area of this triangle, if I know the sides of the triangle, so the area of our triangle is equal to 1/2 base times height, 1/2 times 5 times 6. 2 goes into 6 3 times. 3 times 5 is 15. And the area then of the triangle 3, our area of square 3, is equal to 121 minus 4 times 15. And that's equal to 61 units squared. Okay, now I've got enough information to proceed with this. How are the areas of the three squares related to each other? Well, this is 61 units squared, and let me just try something. 25 plus 36 equals 6 plus 5 is 11, carry my 1 is 61 units squared. Well, I see a relationship here. Do you see it, right? Yeah, okay. So 61 units squared, that tells me that the area of square 1 plus the area of square 2 equals the area of square 3. That looks awfully familiar, right? If we look ahead, we see that indeed this is an expression of the Pythagorean theorem, which is the side 1 squared plus side 2 squared equals side 3 squared. That's the Pythagorean theorem. A squared plus b squared equals c squared. Use the Pythagorean theorem to find the length of the missing side. Okay, we know from the Pythagorean theorem that a squared plus b squared equals c squared. This is a leg sub 1 squared plus leg sub 2 squared equals the hypotenuse squared. Okay, now what do we have here? We've got one leg that's 5. We have the hypotenuse that's 6 and a leg we don't know. So that means I have 5 squared, and I'll just call this b squared, plus b squared equals 6 squared. So 25 plus b squared equals 36. subtract 25 from both sides of the equation, b squared equals 11. So b equals the square root of 11, which is approximately 3.32. Remember, if you're asked to find an exact value, you stop here with the radical at root 11. If you're looking to find an approximation, then 3.32 would be sufficient. Make sure you know which one you're looking for. Okay, I know I mentioned this was long. It was. I do hope it was helpful to you. Good luck proceeding with this and on your mastery quiz. And I'll see you on the next lesson.